Hello friends, welcome to my channel. In my previous video, I discussed about the Gauss law in dielectric, and I also discussed that what are the bound charges in dielectrics. In the present video, I'm going to talk about the Classius-Mossotti equation. This is the equation which actually relates the dielectric constant of a dielectric material to its atomic polarizability. Right. If you have not watched my earlier video, I will give the link in the description box. Kindly do watch because we are going to use concept of bound charges from the previous video in the present one. So let me discuss the Clausius-Mossotti equation. Suppose we have the dielectric material placed in the two parallel plates of a capacitor like this. Suppose these are the two parallel plates that are connected to some sort of a battery having some potential difference V. Okay, let's suppose this is the dielectric material which is filled between these two parallel plates. Let's suppose this is a positive terminal of the battery, and this is the negative terminal. So this is positive plate, and this is the negative plate. So in the last video, we saw that uh, electric field will be generated due to this potential difference between these plates. If the separation between the plates is D, so let's say E0 electric field is created in this direction because of this potential difference V, which is provided by the battery between the plates. Now, since there is a process of polarization in the dielectric, which I discussed in detail in the previous video. So, because of that polarization process, the dielectric will acquire the surface charge density as this. The process of this was already discussed, so kindly refer to the earlier video. So, negative charge will be piled up here, and the positive charge will appear on this surface, and we call that bound charge density, sigma b rather, and I told you that sigma b is was equal to p dot n hat, where n hat is the direction of the area vector, and which is perpendicular to the surface, and p is the uh, polarization, so-called polarization. It means the total dipole moment per unit volume. Okay, so in this case, we are going to discuss the P is uniform between these two places, right? So the direction of P will be from negative to positive of the bound charge, the bound charges from negative to positive. This is the direction of P, and we'll assume that this P is uniform between these two plates. However, we discussed the case of non-uniform P as well in the last video, and I discussed that in that case, not only the surface will acquire some charge density, rather volume will also acquire a charge density when P is non-uniform. I discussed that in detail in the last video. So now our question in the present video is, in the present context, is that what is the electric field that is actually felt by an atom in this dielectric? Suppose I choose a reference atom as A here. So what is the net amount of electric field that is felt by A? Now we see carefully. So E0 is the applied electric field, which is uniform between these two plates. So A will feel E0 also. And there is a net electric field due to the bound charges that we have just seen. Um, this bound charge density, the direction of the electric field, let's say, is E1 in the reverse direction of E0 because of the opposite polarity of the charges. So that will also act on A. So in an average, in the previous video, we considered the net resultant of E0 and E1. We took as E. We took E as E0 plus E1, and we can safely assume that on an average, this is the electric field, average electric field felt by an average atom in the dielectric atom. But is the picture that simple? Because you see, if you take the neighborhood of A, the reference atom A, there are lots of other electric dipoles present due to the polarization process of the dielectric. So it means that A is under the impression or the influence of several other electric dipoles nearby. So the electric field at A is not merely the sum of E0 and E1. In fact, it also feels the electric field created by the other electric dipoles, especially the neighboring electric dipoles. Okay, so now our main question is, which was actually asked by, sort of, dealt by Lorentz, and he calculated what is the actual net amount of electric field felt by a particular atom. Um, in a dense electric specifically. Suppose this electric dielectric that we have considered in this diagram is a rare medium, right? Is where the atoms are not atomic density is not too high. So and of course one can ignore if the dielectric dipoles are very far apart. One can ignore the effect of one on the other. But when the dielectric is dense in itself, it may be a liquid or solid. In that case, it is hard to ignore those influences. It is hard to ignore the influences of the other dipoles, I would call the atomic dipoles, to the reference atom A, for example. So it means we really need to include that as well. So what Lorentz actually tried is Lorentz calculated the what is the local electric field felt by any random reference atom that we have chosen, like A here. So what is the local electric field that is felt by A, which is of course the resultant of E0, E1, and the nearby electric dipoles or the other dipoles present in the dielectric medium. So let me write down that E local, which is felt by A. I'm calling that E local. So that actually this expression was given by Lorentz, which is also called Lorentz local field. That is equal to E0 plus E1. This is the average electric field if we talk about, and we used it in the previous video as E in the previous lecture. Still, we will stick to the same convention, but now what we are doing is we are also considering the effect of other electric dipoles present nearby A. So to calculate the effect of others, what Lorentz applied a technique that he took a spherical cavity. Why spherical? Because it's easy to deal with the spherical geometry because of this uniform in nature, uniform geometry. So it's easy to make the calculation on the spherical cavity. So what he did is actually he considered a spherical cavity centered at A. Let me choose with the red color. And he told that the electric field total net electric field at A will be the resultant of E0, that is the applied electric field, E1, that is the because of electric field produced due to the polarization of the dielectric, plus the electric dipoles present in this cavity area. Suppose you create a fictitious cavity here and you consider now what is the size of the cavity. That's also important. You see, what we are doing here is we're trying to consider the effect of neighboring electric dipoles. So certainly this radius of this cavity is much greater than the atomic radius itself, because if you go really inside an atom itself, suppose this is a picture of an atom that I've drawn. This is a nucleus, positive nucleus. This is electron cloud revolving around the nucleus. So in an atom itself, electric field varies from one point to other point. So the calculating the exact electric field at a particular point is a really tough business. That's why we talk about in terms of the average electric field, and we are very happy in most of the cases by taking E equal to E0 plus E1. For example, we wrote down in case of Gauss law, it took the average electric field as E, which is the resultant of E0 as E1 in the last lecture. But you see, but here the picture is not so simple, because this particular atomic dipole is being influenced by the other present nearby. So that's why we are considering the effect of those, because it is difficult, as I said, in the dense medium to ignore the effect of others. So A will feel E0 plus E1, and suppose I took out this portion, let me shed with red. Suppose I take out this portion of a red portion from this electric material, and there is a cavity here. The size of the cavity is certainly greater than the atomic size, maybe let's say 50, 60 angstrom, so that we consider the nearby sufficient number of electric dipoles present A, okay, in a dense material. So uh, now what what will be the other electric field acting on A? Other electric field will be when you create such a cavity, there will be a charge generated on the spherical cavity itself, and because of the induction process, there will be, let's say, plus charge here, um, and there will be minus charge. Overall, it will be neutral, and because of the electric conduction, this will be the charge. This sort of charge density will be produced on the spherical cavity. What will be the exact amount of the spherical cavity? What is the exact amount of spherical charge density on this cavity? We'll calculate in a short while. But due to this surface charge density produced uh, on the surface of this cavity, the electric field will be uh, at A. Will the effect of electric field be at A. So let me call that electric field as E2, and there is elect there is an electric field at A due to the present of all the atomic dipoles, all the electric dipoles present within this shaded region of red region that I've shown. Within this region, if I shade it with, let's say, this color, uh, within this region, of course, there are other electric dipoles present. The effect of those dipoles also will be at A. So let me take that as E3. So my E2 is electric field at A due to surface charge density on cavity, and E3 is the electric field at A due to electric dipoles present in cavity. Okay, now we are going to calculate this E0, E1, E2, E3, and then we'll be putting back those values here, and we'll get the local electric field. So if we go back to equation 1, so E local is actually equal to E0 plus E1, which we wrote down as E, the average macroscopic average electric field. So this is so this E here is a macroscopic one, because we are talking about the average electric field felt by the dielectric material as a whole in this geometry, in this figure. But when you come to the calculating the electric field by a single atom, the things will change drastically. Yeah? Then we have to really count the effect of other electric dipoles, as I said, by taking the cavity. So E0 plus E1 is E plus E2 and plus E3. So we need to calculate this E2 and E3 to find out the local electric field. Now, if we talk about E3, E3 is the electric field due to the presence of electric dipoles in this green shaded region. Now, what Lorentz did actually, he made a calculation by considering then the crystal structure of the dielectric and taking it to be cubic one. He explicitly showed that E3 actually turns out to be zero for the cubic crystal, for the cubic crystal structure. Right, E3 comes out to be exactly zero. This calculation is given in the, for example, a book like J.D. Jackson. We are interested, you can go and refer there. So, if you consider the cubic structure of the material, so what can be thought that each atom can be thought as a situated at the each corner of the cube, and now each atom is like electric dipole now, and they are identical atom, suppose, and that because we have considered the P to be uniform and they are pointing in the same direction of the same magnitude. Now, because of the symmetry of this structure, if we calculate the electric field at the, for example, origin, then it turns out to be zero, at precisely zero. So E3 comes out to be zero for the cubic crystal. So it means the Clausius-Mossotti equation that we are going to derive from this discussion, that is valid only for cubic crystal. Yes, of course. And in fact, if you think of amorphous material where there is no arrangement as such, so things are completely random, then because of this random nature, again we get the E3 to be zero. Huh. One assumption in this derivation will also be there that we consider this material, dielectric material, to be isotropic. That that the effect of these neighboring electric dipoles is not directional dependent. It is same in every direction. You know, in whichever direction we consider from A, the material seems quite isotropic. So for most of the practical materials, dense materials, their structure is cubic or they are amorphous, and they are isotropic. E3 equal to 0 is a good assumption to work with. So this is the first thing that the Lorentz actually calculated. Then E3 is 0 for cubic crystals, for amorphous materials. Okay. One of the assumptions involved here is that assumption is that dielectric is isotropic. Every direction is same. Okay, so this E3 actually turns out to be 0 for most of the practical uh, substances. For those material for which this condition is not satisfied, of course, the prediction made by the Clausius-Mossotti equation will vary. What is the Clausius-Mossotti equation? I told in the beginning that it is the equation that relates the dielectric constant of a material to this atomic polarizability. Okay, so now our equation relates to E log is equal to E plus E2. So we need to really calculate the E2. E log is equal to E plus E2. Okay. So let me put as number 3. So we need to really calculate E2. And the E2, if we have to calculate E2, this is a standard procedure by which can be done. I mean, it is given again in several textbooks, but we can calculate it right here as well. Uh, so suppose this is the cavity that we are talking about, and this with the plus here charge and minus this side. So overall, this is neutral, and I told that we will be calculating the what is the net amount of charge present on this cavity. You need to calculate that. Okay, only then we can calculate the electric field at its center, which is the at the reference atom A. Hmm. We can only calculate the electric field at A if we know the surface charge present on this cavity. How to calculate the surface charge? I already explained in the previous lecture, and I told it right in this lecture as well, that sigma, the surface charge density, is equal to P dot n hat. Okay, where n hat is the direction in which area uh, uh, vector represents, so the normal to the surface. Suppose I choose this direction, which was the direction of E0 in my original picture. If you see E0 direction, P is also in this direction. My P is also in this direction. My E0 is also in this direction. So I choose the direction to be Z axis, and I take small area element, let's say d omega, at an angle theta from the Z axis. Let's say this is d theta here. So what is the amount of charge on d omega element that can be calculated if I know the sigma theta? That is the at angle theta. What is the surface charge density, which can be calculated as P dot n hat, where n hat is the normal vector n hat, area vector, which is normal to the surface. Now, what will be the direction of electric field at point A due to this surface charge? This will be in this direction only. This will be in this direction only. Okay, because I have to put the positive charge, so it will be in this direction only. Okay. So if I calculate my DE2 prime, I've said it prime because you know, I will have to take this cosine component later on. I will discuss this. Okay, so let me call this DE2 prime. What is DE2 prime? DE2 prime is the electric field due to this d omega element that I have just taken here, surface area, at the center A. So what that equal to? 1 over 4 pi epsilon naught q by r square. What's the charge on this sigma? Charge is surface charge density sigma theta times the area divided by the distance. Let's say the radius of this cavity is r square. Now 1 over 4 pi epsilon. What is sigma theta? Sigma theta is p dot n hat. So what is the direction of p? Direction of p is this. and direction of n is this. Both have the angle theta in between. So P times cos theta, because the magnitude of n hat is 1. So P times cos theta, sigma theta is P cos theta. D omega in three dimensions, the area vector is r square sine theta d theta d phi divided by r square. So what I get as dE2 prime, so let me put a magnitude here. If I want to write the vector form, so I will have to write 1 over 4 pi epsilon naught P uh, cos square, sorry, cos theta sine theta d theta d phi. Okay, so let me put a magnitude here for the time being, and then we can convert into the vector form. So now this is the electric field in this direction, which I've pointed out, dE2 prime. Now I have, because of the symmetry of the problem, because of the symmetry of this spherical symmetry of the cavity, I can choose another element here of the same area at same angle theta and d theta and calculate the de to double prime, let's say, or magnitude wise it will be equal to de2 prime again, and take the component of this de2 prime on the along the z axis. So we see the along the z axis the component will get add up, and all the other component in the other direction will get cancelled out because of the symmetry of the problem. So basically only the component along the z axis of this de2 prime will survive. So in that case, if I want to write down what will be the next de2, that will be 4 pi epsilon naught, or rather, let me write this way. What will be de2? It will be de2 prime time cos theta, and then I have to, if I want to calculate the electric field due to the entire surface charge present on this cavity at A, I have to integrate it with the proper limit of theta. So let me put the values here. 1 over 4 pi epsilon naught P cos square theta sine theta d theta d phi. Okay. Okay. So now I have to integrate to find out E2. So when I integrate it to find out E2, I can, this I have considered P to be uniform, so I can really take that to be out, and I put a vector sign now, and I will be cos square theta sine theta d theta d phi, where phi goes from 0 to 2 pi and theta goes from 0 to pi. Okay, so now I get integration d phi is 2 pi, so I will get 2 epsilon naught here, and cos integration of 0 to pi cos square theta sine theta d theta. Let me put cos theta to be t, so minus sine theta d theta will be dt, and I will have the following. So I have put cos theta to be t, so it will be t square minus dt, and limit will be, since I have put cos theta equal to t, so limit will be 1 to minus 1 and p upon 2 epsilon naught. So if I integrate minus p upon 2 epsilon naught 1 over 3 t cube minus 1 minus 1, that is p over 3 epsilon naught. So my E2 is p over 3 epsilon naught. So I get my E2, E3 is already 0, I've got it, and E0 plus E1 combinedly, I'm calling it E. So now my E location from equation 1, so E log is actually equal to E plus P upon 3 epsilon naught. So this is the local electric field felt by the reference atom A that we have chosen, any random reference atom A that we have chosen. Okay. Okay, so now due to this local electric field E, so there will be atomic polarizability present in the atom. So the dipole moment present in the atom. So this is electric dipole moment of atom at A, right? That will be proportional to this E log, and that is equal to um, alpha times E log, where alpha is called the atomic polarizability. So now if we put this E log, value of E log that we have just calculated from 4, so from 4 and 5, we get P is equal to alpha times E plus P upon 3 epsilon naught. This is equation 6. And we also discussed that the total dipole moment per unit volume, P, that is equal to n times P if n is the number of atoms per unit volume in the dielectric. Because if n is the capital N is the number of atoms per unit volume present in the dielectric, and each atom has the electric moment as small p factor, so the total dipole moment per unit p will be n times p, which is n times alpha times E plus p upon 3 epsilon naught. So if I little bit rearrange the equation 7, I can actually find out the following. Okay, so I rearrange equation 7 a little bit, and we I discussed in the previous lecture, or previous video, that P, the total dipole moment, is proportional to E, that is the average electric field in the dielectric, and which was equal to epsilon 0 chi E, where chi is the electrical susceptibility. And I told in the last time that my chi here is unitless, dimensionless. If you don't write the epsilon naught part, that chi will have the appropriate dimension. But in my notation, the chi is not having any dimension. It's a constant, directly. So in some certain books, they write p equal to chi e, where the chi will have the according, chi will have dimensions accordingly. So now from 7 and 8, if I look, I'm going to get epsilon 0 chi e is equal to n alpha e plus p again, epsilon 0 chi e. So chi e over 3. This is equation number 9, let's say. And if I rearrange question 9 a little bit, so I will get epsilon chi is equal to n alpha 1 plus chi by 3, which means epsilon 0 chi minus n alpha chi by 3 is equal to n alpha, which means if I take the chi common, I get to get epsilon 0 minus n alpha by 3 is equal to n alpha, right, which is equal to chi equal to 3 n alpha over 3 epsilon naught minus n alpha. And chi, as we know, is equal to the relative permittivity minus 1, right? Epsilon r was equal to 1 plus chi, as I discussed in the last lecture as well, where this is relative permittivity, relative permittivity, or just which we call the dielectric constant as well. So I can write down really the dielectric constant minus 1 is equal to 3 n alpha over 3 epsilon naught minus n alpha. So this is, let me call as equation 10. So this is one form of the Clausius-Mossotti equation, which relates the relative permittivity, that is the dielectric constant, to the alpha of the material. There is a much familiar form of this, which can be written as follows: epsilon r. If I add, let's say, uh, 3 both sides, I'm going to get 3 n alpha upon 3 epsilon naught minus n alpha plus 3, which means 3 n alpha plus 9 epsilon 0 minus 3 n alpha divided by 3 epsilon 0 minus n alpha. So this goes away, and I get 9 epsilon naught upon 3 epsilon naught minus n alpha. Equation 11. If I divide 10 by 11, I'm going to get epsilon r minus 1 upon epsilon r plus 2 is equal to 3 n alpha over 9 epsilon 0, which is n alpha over 3 epsilon 0. This is the more famous form, or more familiar form, of the Clausius-Mossotti equation, where epsilon r is of course nothing but the dielectric constant, and alpha is the atomic polarizability. So this equation that we have derived with certain assumption, that we have taken our material to be dense, isotropic, and we have considered the cubic structure or amorphous structure, right? For those materials for which this E3 was equal to 0, right? Precisely the effect of all the electric dipoles within the shaded region comes out to be 0 at A. The electric field due to all the electric dipoles present in the shaded region at A comes out to be 0. For those, all those materials, as for these, all these assumptions are true, we get the Clausius-Mossotti equation as this, which is an extremely successful equation for most of the materials that we have discussed with certain assumption. Uh, right, this gives a quite satisfactory result for most of the liquids and the solid material, dielectric material. Okay, so that's it for. Thanks for watching. Thank you.